Welcome to Chapter 2 of Honors Calc. This chapter is called Differentiation. So we've looked at limits, and now we're going to really start to do some of the heavy-duty calculus in the course. We're going to start taking these things called derivatives, which are related to limits. So we're not really going too far away from that, but we won't be doing the limits in the sense of what we were doing in the first chapter too much, just in the beginning here to introduce the idea. So section 2.1, the first section of chapter 2 in your book, is called the derivative and tangent line problem. And I really want to focus on this idea of the tangent line problem today to kind of motivate you to understand where the derivative comes from and why it works. So the tangent line problem is really one of the biggest issues that led to the development of calculus. Remember, as I've said in class before, calculus was developed to answer questions that mere algebra couldn't answer. And one of those questions was, how do you draw a line that's tangent to a curve at a point? We all know how you draw a tangent to a circle, right? You have a circle, and you just draw that line that goes to the circle at one point that ends up being perpendicular to a diameter, right? That's a tangent for a circle. But what about when you have a curve? What does it mean to say the line that's tangent to like that point I drew there? Well, the way we're going to determine this is we're going to first look at these things called secant lines. Now, secant has nothing to do with the trig function you learned last year in pre-calc. It's a different word, or I should say it's the same word with a different meaning. It's a line that intersects a curve at two places. So, for instance, if I put a second point and I connect these, now I have drawn for myself a secant line. Okay, so we're going to talk about how that turns into a solution for the tangent line problem through the use of a little bit of an animation I have here. Okay, so this is an animation here of really talking about what we mean as far as turning secant lines into tangent lines. So notice you've got that fixed point, P, which is at 2, 4. And notice that I'm taking this point Q, and I'm moving it closer and closer to P. Now, what I like about this animation is it's dynamic. So it's always keeping a line segment between P and Q, the secant line. And notice what happens is Q moves closer and closer and closer to x equals 2 and the point P. That secant line starts to become a tangent line, which is what that yellow line always is. So the yellow represents the tangent line that goes through just point P. And as we bring Q closer to P, all the secant lines start to get closer and closer to the tangent. So this is kind of an intuitive graphical idea of what we mean by trying to figure out what is a line tangent to a curve and what is its slope. Okay, so now that you've seen how we can go from a secant line and a bunch of secant lines to a tangent line, let's start to do some algebra, and then eventually let's bring the calculus in to really come up with solving this tangent line problem. So we want to find the slope of a secant line. So I want to do this with a little bit of graphing and a little bit of algebra based on my graph. So I've got a curve. I'll draw one sort of similar to what was on the animation. Now I've got 2 points. Put one point here, and we'll call that point C, which makes the corresponding y value f of c, because this is the function f of x. And I'll pick a second point, put it up here somewhere. Now, I don't quite know how far away I am from C to this second point. We'll call it point 2 for right now. But I can use some symbols for it. I can call the distance from C to point 2 delta x. So that means that this coordinate is c plus delta x, because I'm going delta x to the right of this point C. That also means the y coordinate would be f of c plus delta x. Okay, so now if I draw the line connecting those 2 points, and I want to get this slope of this secant line, let me draw in a different color, right here. If I want to get that slope, I can use my change in y over change in x formula that I've learned in all my algebra and pre-calc classes. So remember, the change in y, would be y2. In this case, the y value is f of c plus delta x minus y1, which is just f of c, all over, well, it would be the change in x, which is technically c plus delta x minus c, but I'm going to take a shortcut and just cancel the c's out and call that just delta x. The change in y over the change in x. Okay? We call this quotient that I've just come up with using the notion of slope a difference quotient. Okay, you saw these when we did the calculator lab. We saw that there were two of them. To be more specific, this is called the forward difference quotient because I'm picking a second point to the right of my point C. If I picked a point over here and found my secant, then we would have our backward difference quotient. And if I picked a point equidistant from C from the left and right and got those two points into a secant line, that would be our symmetric difference quotient. Okay, your book only talks about the forward difference quotient, so that's what we're going to use here in this presentation. So here we go. Let's connect the animation that you just saw with the algebra using calculus. So remember the idea that we said here. We're going to take this second point, as you saw in the animation, and we're going to move it closer and closer to C and keep calculating all of these different difference quotients, all of these different slopes. And we're going to keep doing that until this second point, this distance delta x, basically is non-existent, i.e., we're going to make delta x approach 0. Uh-oh, he just said the word approach. What do we think that might mean? You guessed it, we got to take a limit. So if we take the limit of that difference quotient as the distance between that fixed point C that we're trying to get the slope of, and the second point that we drew a secant line with, as that distance gets closer and closer to 0, we can figure out the slope of the line tangent to the curve at C. I should add that to this. Okay? And here's the definition of it. So we're saying the limit as delta x approaches 0, which is the distance between the 2 points of my secant line. It's the limit as that distance approaches 0 of all my secant slopes. That's what delta y over delta x is representing here. These are the secant slopes, which then I broke down, and your book also breaks it down, into the difference quotient that I talked about in the last slide. And I got this, if you want to look at this again in your textbook. This definition comes from page 99 of your book. There's some pictures there as well if you want to take a look at them. Okay? All right, so now we want to use that definition from the last slide to see if we can come up with some slopes of tangent lines at some given points for some given functions. So we want to find the slope of the tangent line of y equals 3x plus 2 at the point 2, 8. So remember what our definition said. It's the limit as delta x approaches 0 of this difference quotient f of c plus delta x minus f of c all over delta x. And in this case, c is 2 and f of c is 8. So we're doing the limit as delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x. All right, so remember our function notation. This means we're going to take this whole 2 plus delta x and plug it in for the x in the equation. So I get 3 times the quantity. Actually, I need that limit statement because I still have not plugged in 0 for delta x. 3 times the quantity 2 plus delta x plus 2 minus, and f of 2 is right there, 8, all over delta x, which now I have the limit as delta x approaches 0 of 6 plus 3 delta x plus 2 minus 8 over delta x. Now, let's start to clean things up. I've got a 6 plus 2, which gets me 8, but then I have a minus 8. So these three numbers cancel out. Now I'm left with 3 delta x over x. Look at that. The delta x's cancel out. So I don't even need to plug in a limit, or plug in 0, because it's the limit as delta x approaches 0 of 3, and we know that the limit of a constant is the constant. So the slope's got to be 3. Okay? How about you try the second one, the slope of y equals negative 2x plus 1 at 0, 1. Pause the video, and when you're ready to see me do it, pick up where we left off. Okay, so same idea here now. C is 0, f of c is 1. So I want the limit as delta x approaches 0 of f of 0 plus delta x minus f of 0 all over delta x. Now this is an easy one because 0 plus delta x is just delta x. So we take the delta x, plug it in for the x in the equation that we're given. We get negative 2 delta x plus 1 minus the 1 here because that's f of 0 all over delta x. We want the limit as that approaches 0. Well, look, plus 1 minus 1 cancels, so I'm left with the limit as delta x approaches 0 of negative 2 delta x over delta x. The delta x's cancel out, so I get the limit as delta x approaches 0 of just negative 2, and that is also negative 2 because it's a constant. Okay, when they're linear like this, it's pretty straightforward. But now let's look at what happens when they're not linear. So I want to get the slope of the line tangent to f of x equals x squared plus 2, a nice parabola, at c equals negative 1 and c equals 2. You don't have to draw it, but if you're a visual kind of gal, there's your graph. I want the slope here at negative 1, so I want the slope of that line. And then 2 is about here. I want the slope of that second line. So we can use this definition. We'll do it for 2 separate problems. So let's try it for negative 1. So for c equals negative 1, we want the limit as delta x approaches 0 of f of negative 1 plus delta x minus f of negative 1 all over delta x. Okay, so I'll take that expression, plug it in for the x here. So now I get negative 1 plus delta x squared plus 2 minus f of negative 1. Well, when I put in negative 1 squared plus 2, I get 1 plus 2, which is 3. So I have minus 3 here, all over delta x. Now, I got to deal with this piece, so I have to do some foiling, and I get the limit as delta x approaches 0 of 1 minus 2 delta x plus delta x squared plus 2 minus 3 all over delta x. Okay, again, I have some cleaning up I can do. I have a positive 1, a positive 2, and a negative 3, so they can all get canceled. So I have the limit as delta x approaches 0 of negative 2 delta x plus delta x squared all over delta x. And look, I've got delta x's in both of these terms, so why don't I factor them out? Limit as delta x approaches 0 of delta x times negative 2 plus that other delta x, because I had 2 of them here. Really, there should be parentheses around that so you can see that it's not just x squared, it's delta x squared all over delta x. Now I can cancel those delta x's out, and I get the limit as delta x approaches 0 of negative 2 plus delta x, which is an easy limit. I just take the 0 and plug it in for the delta x. Negative 2 plus 0, which is negative 2. Okay? See if you can try the same thing for c equals 2. Again, pause the video, and when you're ready to see how it's done, pick up where you left off. Okay, for when c equals 2, now I have my limit as delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x, which is the limit as delta x approaches 0 of, okay, 2 plus delta x squared plus 2 minus whatever f of 2 is, and in this case f of 2 will be 6, 2 squared plus 2, all over delta x. We got to put on our foil hats again. I get 4 plus 4 delta x plus delta x squared plus 2 minus 6 all over delta x. All right, let's clean things up. 4 plus 2 is 6. Minus 6 makes 0, so they can all get canceled out. We get the limit as delta x approaches 0. I can factor out one of those delta x's and be left with 4 plus delta x all over delta x. Cancel out the delta x's outside, and I get the limit as delta x approaches 0 of 4 minus delta x, which then when I plug in 0 for delta x leaves me with the 4, which is the slope at that line, of that line at that point. Okay? I hope this helped a little bit, get you an idea of how to find these tangent lines, figure out graphically what they mean, algebraically how to write their slopes by taking a bunch of secant lines and finding the limit as the distance between the points becomes 0. I have some examples for you to try like these. Give them a try, and then this is where we'll pick up next class. Okay, if you have any questions, feel free to let me know. Thank you very much for watching. I hope you enjoyed.